We'll talk today about magnetic force on a current carrying wire. Basically, we have a wire, current circulating in this wire, and there is a magnetic field applied. How this wire will react to the magnetic field. So there is an experiment shown in the figure here. If you take a vertical wire and a magnetic field is pointing toward you here, out of the plane, if there is no current circulating in the wire, nothing will happen. But as soon as you apply a current, let's say a vertical current here, the wire will bend to the right. If you apply a current in opposite direction, going down, the wire will bend to the left. So I share with you a link of an experiment showing that how a wire can bend up and down if we change the circulation of the current. I'm about here to explain you why the wire is bending like that. So in the figure here, I draw just a zoom of this wire. So let's say the wire has this shape. It has a length L. And the current is, let's say, going up in this wire. The current is moving up. The current is just a positive charge. It's charged over time, so we can imagine that we have a positive charge here, Q. And this positive charge is moving upward. So the charge, it will have a constant velocity called drift velocity. That's what we learn in current and resistor chapter. So the charge is moving with constant velocity called drift velocity. And in this region, we have basically magnetic field, uniform magnetic field, by the way, B, out of the page. What is the magnetic force applied on this charged particle by using a hand rule? The force, it will be toward the right. That's the magnetic force. So the charge will move toward the right, so the wire will bend toward the right, like in this figure. All right, so let's write now the equation of the force of this charge. So the force, it will be just Q V B, let's write the magnitude, sine phi. Of course, in the figure here, phi is just 90 degrees, but just I will write the general equation. What is the charge? Charge is just current multiply time. What is this drift velocity? So if the charge moves from here to here with the constant velocity, what is that velocity? That's just length, the distance per time, b sine phi. So in other words, that's just current times length times b times sine phi. That's the magnitude of the magnetic force. If I want to write this force in vector form, so I will write it just like this. The force is equal to what? Current is a scalar. The length, I can write a length vector, distance vector, L cross B. What is L? That's a vector going, the magnitude of this vector is just the distance L, and the direction of the vector is direction of the current. So if I do L cross B, I multiply that by the current, I get the magnetic force. So this force, when I can use it, there are conditions. I need to have, like I draw here, straight wire, and, like I said in the beginning, uniform magnetic field. If one of these conditions is not fulfilled, I cannot use this equation. So to be able to use this equation, I need to have a uniform magnetic field and a straight wire. What is the general formula of the force? So the general formula when B is not uniform, or when wire is not straight. Well, let me take an example of the second condition. Let's draw just wire like this. That's my wire. Okay. And I have, let's say, a magnetic field. We draw magnetic field lines. That's a magnetic field. Okay. So let's assume magnetic field is uniform here, but the wire is not straight. So what is the force? Well, this wire I can still divide it into tiny pieces. And this piece of length dl and this piece of wire is straight. So what is the force on this tiny wire? Well, I can call it df equal I dl cross b. And you guess it right, what it will be the force, the total force on the wire, so that's the integral on the wire of what? Of this tiny force, I dl cross b. Okay, so let's take here a practical example. So here we have a sample problem about how to suspend a wire, current carrying wire, by using a magnetic field. So basically we have here a wire, a horizontal wire. There is a current flowing in this wire. The wire, it has a mass, m. It has a length, L. So we are given the ratio mass per length, which is a linear density. And we are given the current, which is 28 ampere. The question is how to suspend the wire. So basically the wire, since it has a mass, there is weight, m times g. That's the weight of the wire. So eventually the wire will fall down. So I want to suspend the wire. How to do that? I need a force, opposite force, equal in magnitude and opposite in direction. How I can create this force? By using a magnetic field. So I want a magnetic force to be upward. The current is in from left to right. So let me write the equation of the force. The force equal I L cross B. L, that's the vector L. So I want L cross B equal F, and F is upward. How I do that? I can use the right-hand rule, and the right-hand rule will tell me if my temp should be oriented vertically, the vector B should be into the plane. That's the direction of the magnetic field that I need to apply. Now, what is the magnitude of this field? Well, the magnitude of the force. What is the magnitude of the force? That's A L times B, because in this schematic I choose B to be perpendicular to L. So the angle between them just 90 degrees, sine of 90 is just 1. And this force has to be equal to what? To M times G. What is G? Is the gravity. So from that I can get the magnitude of B, which is mg over IL. I can reorganize this, so that's mass over length, which is given here, times g over I. So what is the mass over length? 46.4 grams. So gram, I need to convert it, 10 to the power minus 3 kilogram per meter. J, that's 9.8 standard unit, and current is just 28 ampere. This will give me 1.6 10 to the power minus 2 Tesla. All right, thank you for watching. See you next time.